Morning all. So in the last class, we were discussing about the flow chart of the sinter making process. As we have discussed that there are various raw materials which are used for sinter preparation, like iron ore fines, fluxes like limestone and dolomite, and we use coke grease. And apart from that, we also use the sinter returns. And all these are having different size ranges. The reason why we use different size ranges because if you see the iron ore, its range is not more than 10 mm. Whereas similarly, coke and limestone, their size is also less than 3 mm. So the reason for maintaining this size range is maintain an adequate voidage as well as an efficient heat transfer takes place during the sintering process. If suppose these size ranges are very large, then there is a possibility of local overheating may take place, and that leads to formation of high temperature phases, and sintering cannot take place effectively. And because of this non-uniform heating of the intermix, the properties of the sinter, final sinter which is produced, that may be deteriorate. Not only the iron ore or coke, fluxes like limestone and dolomite also, we need to maintain an absolute size range so that its dissociation during the, which is an endothermic process during the sinter making, will take place effectively. Now you can see the various parts of this information. So we have storage bins, where you can see in this particular picture, this is one of the storage bin. Like that, a series of storage bins will be present at this particular location. You have a mixer, that is your MND, that is mixing and normalizing drum, and then you have a feeding system is there. And, you have an ignition hood, so the initial combustion takes place, the top layer. Then you have a series of pilot cars which will be moving on the rail. Then you have a charge leveler, beginning of your, or it is in front of the hooper and the drum. Then you have a sinter breaker, that is at the end of the intermission. Followed by, you'll be having a screen and the annular cooling system. And you have a spillage collector, followed by you'll be having wind boxes and dust extractors, exhaust fans, chimney, etc. So these are some of the um, parts of this information and its accessories. We'll see what is the role of each accessory, what you have. First thing is the storage bin. So whatever the raw material which we have received from RMH's department, the raw material handling system department, through the conveyors belt, it will reach to the central plant, and there all these raw materials will be stored in the silos, or you can also call as the storage bins. And from these storage bins, the raw material is weighed amount of raw material will be transferred to the mixing and modularizing drum conveyor belt. And this, if you see the dimensions of this MND, that will be of around 15 meters length and 4 meter in diameter. So in this drum, the entire mixture, the raw material mixture, will be charged, and certain amount of water is also added, and then the drum will be rotated at a particular RPM to produce balls. And the size of these balls or nodules, the size of the nodules will be of around approximately 3.5 mm. The residence time of the charge in this mixing and nodulizing drum will be of around approximately 7 minutes. And then if you see the ignition hood, which is used for the sintering of the top layer of your sinter bed, and this will be ignited through fuel, the gaseous fuel, or some of the oil. So here we use BF gas or furnace oil, and along with that there is a provision for the inlet of the air for the combustion takes place. And you'll be having a side nozzle system will be there inside the oven. We can see in this particular picture, this will give an idea that there is an air inlet is there, and we have side burner system is there. And as I said yesterday, that there is an annealing hood which is located just next to the ignition hood, because once the top layer of the sinter bed comes out of the ignition hood, and the top layer will be having a temperature approximately around 400 to 39 degrees centigrade. When it suddenly coming out from the ignition hood, it will expose to the ambient atmosphere, because of which there is a possibility of large temperature drop may take place. And this sudden drop in the temperature of your sinter bed, top layer of the sinter bed, may lead to deterioration of the properties of your sinter. So to avoid that, if we provide annealing hood, so that we can maintain that, we can minimize that delta T during its traveling. Then the next one is the pallet. This is the pallet. A series of pallets are moved or arranged or moved on the rail system, and these pallets basically supports your sinter bed. This is the one on which your the sinter mix is charged. And these pallets are basically consisting of a series of grade bars, which you can see very clearly here. Series of grade bars are there, which is basically made of high chrome cast iron. And the dimensions of this pallet, if you see, is having approximately 3.3 meter width and 1 meter height and 7 meters of length. And the total length of this entire sinter bed will be of around approximately 68 meters. It may vary from plant to plant, but figures are with respect to our single group. Then the next one is the charge leveler. As I told you, as I shown you in the previous class, this is the charge leveler, which is used to maintain a uniform height of the sinter bed. To maintain uniform thickness of the bed, the charge leveler is used. Then you have a sinter breaker. You can see this is the sinter breaker, where you have a series of prongs are mounted on the shaft, and this will be in the rotating motion. And as the sinter bed moves to the discharging end, the entire red hot sinter will fall onto this sinter breaker, and because of the impact between the prongs and the surface of this, the size reduction will take place. And the broken sinter is crushed and screened, and the oversize is basically subjected for the annular cooling process to further proceed for its application. And the fines, whatever are generated, or the undersized particle, normally of -5 mm size, whatever are there after screening, that will be recirculated, that will be reused as a part of earth layer. Then spillage collector. You can see here in this particular picture that below this center bed, you have wind boxes, and these wind boxes are not located exactly below the vertically, not exactly vertically below the center bed, but it is extended outwards. It's just extended outwards like this, so that the bed, whatever it is moving in the reverse direction, below that you will be having the spillage collectors. So this, the purpose of the spillage collector is that when the bed is moving, there is a possibility that some of the sinters may stick between the grate bars, and when it is moved to the discharge end, and when it is moving in this direction, in this condition, when it is moving in the downward direction, whatever the sinter particles which are stick to the grate bar, between the grate bars, will fall down. So that is basically collected in one particular bin, that is called as spillage collector. And all these are, again, you can reuse it as a part of sinter returns. Then you have wind boxes. As I already told you, these are the wind boxes which are located below the sinter bed. And here there will be a thermocouple at each center, at each wind box, which gives the temperature of the heat which is traveling along with the amount of dust. And at all the wind boxes, a series of wind boxes, you can see here, a series of wind boxes are arranged at the bottom of the center bed, and all these wind boxes are connected to a single common pipe. You can see like this, a single common pipe, and the waste heat along with a number of dust is subjected to the suction, and it will travel towards the dust collector. Is here you will be having some ESP, offshore evaporator, and where your dust and the waste heat will be separated, and the waste heat further is allowed to release out to the chimney. Dust, whatever it is collected here, again you can reuse it within the plant itself as a source of Fe. Yeah, this is the process flow diagram of our plant, Tiger. So you can see starts with the RMHS department, is raw material handling system, where we receive the raw materials uh, from various raw material storage area. Through the conveyor belts, it will reach to the department, and where it is basically stored in the silos, and whenever it is necessary, a proper amount of a weighed quantity of raw material will be sent by, we have a wave feeder system will be there, where they measure the quantity, and then same amount will be transported to the conveyor belt. And all the raw materials, you have a series of storage bins will be there, and below that you will be having a common conveyor belt will be there. So a weighed amount of all these raw materials will be passed on to the conveyor belt, and that belt will be moved to the mixing and noduling drum, where you can see that around 7 to 8% of moisture is added roughly, and then it will be subjected to the ignition process. Where the sintering takes place, and the sinter cake, whatever we are obtaining at the end of, at the discharge end, will be of around temperature 500 to 600 degrees centigrade, and that will be cooled on an annular cooling system to a temperature of around less than 100 degrees centigrade, and after crushing. So the the the, the sinter size, whatever we get it, will be of around will be around roughly up to 400 mm size, and that will be subjected to the screening operation. Then after screening, we basically consider size of around 5 to 40 mm sinter. So this 5 to 40 mm size sinter is further is transported to the blast furnace department, and the undersized, that is less than 5 mm, whatever it is there, that is returned back, and it is used as a return sinter as one of the raw material for making the earth layer. So as I was saying, that if you see in this particular picture, it's clearly mentioned that initially there is a around 50 mm thick layer is basically formed, that is called as earth layer. That is the first layer which actually falls onto the pallet, making a bed of 50 mm with the return sinters, and then that 50 mm return sinter bed will further move, have a fresh feed of around 650 mm. So generally, in our plant, we are making a sinter bed of thickness around 700 mm, out of which 50 mm will be of the earth layer, and the rest 650 mm, whatever it is there, that will be the fresh fresh sinter mix. The purpose of maintaining the hearth layer is to improve the life of the grade bars, because when you are doing the sintering process, the flame front will move from the top surface and slowly it will move to the bottommost part. So when that high temperature reaches to the grade bars, if it is directly comes in contact with the grade bars, then there is a possibility that the deformation of the grade bars may take place, that leads to the gap between the grade bars, a great gap between the grade bars. And if the gap is formed, then larger gap is formed, then the sinter mix cannot settle on this pallet. So to maintain a good life of this grade bars, we are protecting this with a 50 earth layer. And once you have made this 700 mm thick sinter mix, that bed will move continuously like a chain at a desired rate from feed end to the discharge end. Once the mix is fed onto the pellet, then that bed will move through the ignition zone, where we call it as start of the ignition, where the topmost layer of the sinter bed will expose to the sintering temperature, and the localized ignition or localized incipient fusion of the sinter mix may take place, and rest of the layers, whatever are there, that will be undergone sintering once the bed is moved out of the ignition hood. The rest of the layers will be get ignited through the suction process. As we have the fuel at every part of your entire sinter bed, as we have seen in the beginning slides, the raw materials where you have cook grease. This is acts as a fuel, and once it undergoes combustion, enormous amount of heat will be generated, and that will be helped in the localized of the iron bearing material. Okay. So the air is basically suction under the stand, so that the flame front after ignition will travel through the entire bed of the sinter mix. So if you see, this is the schematic, the diagram of your sinter bed. Basically, sintering process is just like a puffing of a cigarette, where in general what we do is that we ignite the cigarette at one end, and the other end uh, it will be inserted in our mouth, and if you do the suction, then the cigarette get consumed, right? And also if you see the one end of the cigarette, what we are keeping in the mouth, there you have a cotton puff will be there. That is closed cotton porous puff will be there. Okay. But the other end of the cigarette where we are lightening, there it is open. But the other end of the cigarette, if you see, which we are inserting in the mouth, there it is a porous cotton puff will be there. Right? So here the porous cotton puff, whatever it is there, that actually helps us not to expose the heat to come in contact with our lips, right? So in that way, even though we are doing the puffing of the cigarette, so your lips will not get damaged. Same way, how this cotton puff is acting, the the hearth layer, whatever we have made, the 50 hearth layer, that will similarly acts just like the cotton puff in the cigarette. And it is basically sintering is just like a puffing of the cigarette, sinter mechanism. So here what is happening is that the air, whatever it is present, the top of the bed, when the bed is moving, a 700 thick bed is moving, above that bed, there is a ambient atmosphere is there, there is the air is there. So what we are doing the suction from the bottom of the bed, wind boxes, and we are trying to do the suction of this ambient air which is above it. And when that ambient air comes in contact with your the combustion zone, combustion basically takes place, and it is traveling continuously downwards. The combustion zone is traveling continuously downwards, and it is trying to sinter each layer. So due to suction, hot air flows through the sinter mix, heating the charged material and setting off the combustion zone. That is, we reach the maximum temperature just because of this particular reaction. Carbon reacts with oxygen, which is present in the air. The carbon is nothing but the source of the cook. Cook grease is the source of the carbon. So this, when it comes in contact with the oxygen, it forms CO2. This is an exothermic reaction, an enormous amount of heat will be generated. And that heat will helps in the sintering of your iron bearing material. So if this is the schematic diagram of sinter bed after certain time of the ignition. You see here, when the sinter bed is subjected for the ignition hood, combustion zone will be at the top layer. But in this particular picture, combustion zone is here, somewhere at the center of the bed. That means the sinter bed is already moved away from the combustion zone. So that's why combustion, it is moved away from the ignition hood. That's why the combustion zone is somewhere here. So this combustion zone, initially when the bed is under the ignition hood, the combustion zone is here. When it is moving away from the ignition hood, the combustion keep on traveling like this, and finally it will reach us to the bottommost part. And that will, when it reaches to the bottommost part, the temperature of the bottommost layer you can observe in the wind boxes where you have a thermocouple is inserted, and that will decide the end of the sintering. That is called as burn through point. Now, if you see the thermal profile of the sinter bed, wherever you have a combustion zone is there you have a maximum temperature will be there. Combustion zone is the reason where you have a maximum temperature. Okay. And the layers above the combustion zone will undergo cooling, and the layer below the combustion zone will undergo drying and preheating. Because here we have two zones will be there. One is the combustion zone, that is we call it as a flame front. Other one is the heating zone, which follows the combustion zone from the back. So flame front and the heat front. The flame front is the zone of maximum temperature in the bed, and the heat front is the zone that follows behind the flame front and absorbs that heat. And that is how these layers will undergo cooling, And when the combustion zone is moving, layers before the combustion zone will undergo preheating and drying operation, because we are doing the suction from the bottom. So there is a continuous heat supply will be there for the layers which are front of the combustion zone, and at the top layers will undergo cooling, because as you are doing the suction, cold air, when it comes in contact with the red hot bed which is above the combustion zone, certainly there is a heat transfer takes place here. So here the mode of heat transfer what is taking place, you see, it is convection mode of heat transfer, where heat is traveling from the bed to the ambient atmosphere or to the air, and the air is getting preheated, and that preheated air comes in contact with the combustion zone, and again temperatures are reached, because the combustion zone is already having certain temperature, and this preheated air, when it comes in contact with the combustion zone, and when these two get matched together, then you will attain a maximum temperature. And then that heat, because the suction is taking place continuously, that air is traveling till bottom, and it is trying to preheat the layers which are in front of the combustion zone. So whenever the sintering is taking place, the layers before the combustion zone will always experience drying and preheating phase, whereas the layers after the combustion zone will undergo cooling. So this is a simultaneous process which takes place. So the sintering process basically takes place layer by layer into preheating of the sinter mix, followed by the combustion. The combustion zone moves to the next layer. If those layers are already preheated to the maximum extent, then the combustion temperature at that point will be maximum, which results in the good bond formation and gives a superior sinter. This can be ensured only when complete heat exchange between the gas and the solid basically takes place during firing. It is a completely heat transfer phenomena. We will attain the maximum temperatures only when the complete amount of heat is transferred from the gas to the solid. So that is nothing but the matching. So if the rate of preheating is equal to rate of velocity of the frame front, so this is basically we refer to as matching. There is a concept called matching and mismatching on the center bed that we will discuss in the next class.